Hi guys, this is Alex, and today we will take a look at the first video in the series on physics, and we will be talking about vectors today. Now, there are two categories of quantities in which we can categorize quantities into in physics, and those are the vectors and the scalars. So the main difference between the two is that vectors contain both magnitude and direction, while scalars only have magnitude. Now, what does that mean? Well, let's take a look at a couple of examples. So magnitude is basically a number. So if I have, say, let's talk about temperature, for example. So, temperature is a scalar because it only has a number. So if I asked you how hot it is today, you'd probably tell me it's 30 degrees Celsius out. It probably wouldn't make sense for you to say it's 30 degrees Celsius north, right? So you don't want to talk about direction when you talk about temperature. Whereas if you are talking about something like a force, for example, a direction would make sense because pushing a box north and pushing it south would result in different outcomes for a situation. Another scale that we can talk about is distance. So if I take a walk around a park, let's say here's my park, and I start here at point A and I end up here at point B, and the distance I walked is maybe 5 kilometers, right? So that's my distance. My distance is 5 kilometers. While if I would have asked you what your displacement was, you would tell me that the displacement is maybe only 1 kilometer, right? That is my displacement. Now, when it comes to vectors, we only care about where we start and where we end. I started at A and I ended at B, and the distance between the 2 points is 1 kilometer. So it doesn't matter what I did in between. All that matters is where I started and where I ended, and I'm representing it using an arrow to show the direction I went in. Went from A here, and you can see the arrowhead here showing I went 1 kilometers in approximately an east direction. So we have another vector, the equivalent of distance, which is the analog of distance in scalar world, which is displacement. Another thing we can talk about is speed, for example. So I have an Olympic track here, and here's the starting and ending point. So let's say the track is 800 meters, and it took someone 80 seconds to run around the whole track. So if you ask them what's their speed, then you just simply take how far they went divided by how long it took, and that would be their speed, which in this case happens to be 10 meters per second. However, if you would ask someone their velocity, or rather their average velocity to be exact, then the definition of average velocity is the total displacement over the total time taken. Right, so the point here being that speed is my scalar, so let's call that the scalar because direction doesn't matter, and with velocity I have this thing, displacement. So if I started here and went around and ended up in the same place, what would my displacement be? Well, remember, for a vector, all that matters is where you started and where you ended. Since I started here and ended at the same place, to someone who wasn't looking at what I was doing in between those 2 points, they would think that I didn't go anywhere. So my displacement is 0 meters because I started and ended on the same point, while the time would still be 80 seconds. And in this case, my average velocity is 0 meters per second. Of course, while I'm moving, my velocity is constantly changing, right? Because while I'm here, I'm probably running in that direction, and then around here, I'm running that direction. So the so-called instantaneous vectors, which I'm showing here in the dark blue arrows, is changing, but the average velocity isn't. And the reason why the instantaneous velocities are changing is because their direction change, right? So here we see again another feature of vectors, which is that because they are both magnitude and direction, if either one of the direction or the magnitude changes, then we consider that the vector itself is changing. So I can add velocity to my list of vectors. All right, let's take a look at another example here. Sometimes it might make sense to talk about how fast my speed is changing or how fast my velocity is changing. So if I have a car and it's initially going at 60 kilometers an hour, and then a little while later it's moving at 100 kilometers per hour, and it's sped up in a time of 60 seconds, let's say. So it took the car 60 seconds to go from 60 kilometers per hour to 100 kilometers per hour. Well, the acceleration, so-called acceleration, is what the velocity of the car is finally, or in this case the speed, 100 kilometers per hour, minus what it was before. So that's going to tell me that the car went up by 40 kilometers per hour in a span of 60 seconds. So you get 40 over 60 kilometers per hour on top and seconds at the bottom, which gives me 2/3. So this is telling me that every second the car's velocity is increasing by 2/3 kilometers per hour, so that after 60 seconds it would have gone up by 40 kilometers per hour, and if I add that to the initial 60 kilometers per hour, I find that the car is now moving at 100 kilometers per hour. Now acceleration is generally considered a vector because, as we'll see in later videos, the direction does matter for acceleration. It could result in different consequences, which I won't go into right now. So there we have our examples of scalars. And next thing we need to do is we need to understand how we can represent vectors and how we can add and subtract them, because that's going to be useful for our later purposes. So let's do that. Let's now take a look at how we represent vectors and some of the things we can do with it. So typically for a vector, the length of the vector itself represents the magnitude, meaning the number associated with the vector, and we put an arrowhead to indicate the direction in which that vector is pointing. I'm going to call this vector A, and to tell people that I'm talking about a vector and not a scalar, I'm going to put a little arrow on top. Alright, so the first thing to note about vectors is I can take A and move it all the way onto this side of the paper, and if I keep the magnitude and direction the same, it is still the same vector. It's still called A. So the first rule is that I can move vectors around on the page and they're still the same thing. The next thing I can do is I can think about what happens if I multiply a vector by -1. So I'm going to call this vector -A. Now I'm going to get the vector of the same length. However, it's now pointing in the opposite direction. So it's actually a different vector now because it's pointing in a different direction, but it's pointing in the exact opposite direction with the same length. So I'm going to call that -A. And one other thing we can do is if I were to multiply a vector by some scalar, let's say 2, I'm going to get a vector pointing in the same direction but twice the length as the original vector. So this works with any number, not just integers. So let's get to figuring out how we can now add vectors, let's review how we may add scalars first so that we can see the difference between adding a vector and a scalar. Let's say I have a scalar number 4 and 2, right? It could be any scalar quantity, for example, temperature, and I'm always going to get a 6. So when you add scalars, you only have one outcome. However, for vectors, adding a 4 and a 2 doesn't always give me a 6. For example, if I have a box here and I have two people pulling, one person pulls with a force of 4 newtons, another person pulls with a force of 2 newtons, then we can say that there's a force of 6 newtons to the right. However, what happens if they now pull on opposite sides of the box? One person pulls with 4 newtons here, and another person pulls with 2 newtons in the opposite direction. I hope it's obvious that there will be a net force of now 4 newtons minus 2 newtons, which is 2 newtons to the right. Right? So depending on what direction these vectors, these arrows are pointing, I could get different answers, and I would get yet a different answer if, for example, someone pulls with 4 newtons here and another person pulls with 2 newtons at like some funky angle here, and you'll see that you're going to get an answer that's again different. So the whole point of this is to say that you shouldn't add vectors like you do scalars. So the next question to ask is, how then should we add vectors? Well, there are two methods. They are actually equivalent, but I'll show you the first method, and the first method is called the tail to head method. And the reason will become obvious in a minute. So let me just draw up two vectors on here. I'm going to have a vector right here, and let's have b vector pointing down that way. So how do I add these two vectors? Well, you can think about an example. Let's say we're talking about displacement, right? So let's say I'm in a park, and I walk, I walk from the entrance of the park to the waterfall, and it takes me there. I'm just moving A over. Remember, I can move vectors around and still keep them the same. And then from the waterfall, I'm going to walk over to where the deers are grazing. So that's right over here. Now, for vectors, I don't care where I started. I don't care what happens in between. All that matters is where I started and where I ended. Since I started here and ended here, my resultant, as they call it, is going to go from all the way from the tail of A to the head of B, because the tail of A is where I started and the head of B is where I ended. So we call this A plus B, and the name for it is the general name for it is the resultant. So the resultant of A and B is A plus B, represented by this vector here. Right, let's look at the second method we can use to represent vectors. And this method is called the parallelogram method. And the way this method works is that you take your two vectors, beg your pardon, take your two vectors, take your vector A, and then you take your vector B, and you put the tail of B right where the tail of A is. So you make the tails meet up. And then I complete a parallelogram based on those vectors. So I'm going to draw another vector parallel to A on this side, and I'll draw another vector parallel to B on that side, and they are in fact the same vectors because you can move them around. And what you do is you join the tail where they meet to the exact diagonal opposite of the parallelogram. And this, once again, is a plus b. Now I hope you can see that it's clear from these two diagrams that these two methods are in fact equivalent, because I could just as well have completed the parallelogram here, which a vector parallel to b and a vector parallel to a here, and I would end up with the same resultant as I do with the parallelogram method. So these two methods are equivalent for adding vectors. Now that we know how to add vectors, we can use similar techniques to learn how to subtract vectors. So I'm going to show you that adding vectors and subtracting vectors are in fact exactly the same. So let's start with the same two vectors I had earlier. I had an A, albeit in a different color now, and I had B. Now someone asks me, how do I do A minus B? Well, let me rewrite this so that I can turn it into an addition. So you know that I can always write a subtraction as an addition by saying that I'm going to add A to the negative of B. So remember what happens if I multiply B by minus 1? I get a vector of the same length as B, but now pointing in the exact opposite direction. So that's minus B. So we already know how to add vectors, and this is a simple vector addition from here on. So I'm going to take A, and to A I'm going to add minus B. So remember how we do that? We start here, go to here, and then from here I'm going to there. You put the tail of B on the head of A, and now you join where you started, which was the tail of A, to where you end up, which is the head of B, and we can now call that resultant A minus B, because A plus minus B is the same as A minus B. So I've now subtracted two vectors by adding them. Now let's go back and take a closer look at how we can represent vectors. So this is a closer look. Now we know that we can represent a vector by drawing a line in space proportional to the magnitude of the vector and an arrow pointing in the direction the vector is going. But what if we wanted to tell someone over the phone, for example, what the vector is? Well, it's not so straightforward in that case, because now, it's not so straightforward in that case because now I can't draw a picture and show him where it is. So we will use a Cartesian coordinate. So I'm going to put this vector with the tail of vector at the origin of a Cartesian coordinate system, or at the origin as best I can. So I'm going to call that the x direction and the y direction. Now I want to start right here and I want to end up here. So it doesn't really matter what path I take since it's a vector, right? I could go any path, right? I could start here and then go here and end up here, and that would be the same vector assuming we allow curly vectors, but that's a bit complicated. So what I'll do is I will instead use straight line vectors to get from the tail of that vector A to the head of that vector B, and the way we're going to do that is something like that. I'm going to start here and I'm going to walk to the right in the same direction as the x direction, and I'm going to walk straight up. So as you can see, this green vector here, which I will call A, can be represented by these two other vectors, which I will call B and C. So I can say that A is the same as B plus C, right? Because I started here and I end up at the same place. Now I want some consistent way of being able to write these so-called B and C vectors. So I'm going to introduce something called a unit vector. Unit means 1. So a unit vector has length 1. I'm going to have two special unit vectors. I'll have a unit vector that points in the x direction, and I'm going to call that x. But instead of writing an arrow on top, I'm going to make it wear a hat like that to show that it is of length 1. So that's what that hat there means. And I'm also going to create another vector which I'll call y hat, which is a unit vector, a vector of length 1 pointing in the y direction. Now I can create any vector from just these two vectors, because you know that if you multiply a vector, you get a vector whose length is that many times the length of that vector. For example, if I want to write 3x hat, that would be a vector that's 1, 2, 3 units long, pointing in the x direction. And if I want a vector that is, say, 2y hat, that would be a unit vector that would be a vector of length 2 units long, pointing in the y direction. So going back to here, I can represent B as, let's say, 1, 2, 3, 4, 5. So I'm going to call B 5x hat. And C is 1, 2, 3 units long, and it's pointing in the y direction. So I'm going to call it 3y hat. So writing these down here, B was 5x hat, and C was 3y hat. So my A is now 5x hat plus 3y hat. So now we've solved the problem of telling our friend over the phone what the vector is. I can just tell him 5x hat plus 3y hat, and he can happily go away and reproduce the same vector on his paper without me having to show him a diagram of what that vector looks like. Now this representation of the vector that I've shown you is called the Cartesian representation of a vector. Now I'll be able to simplify addition and subtraction somewhat by using this representation. So let's say I have a vector, let's call it A is 3x hat plus 2y hat, and I have B being, let's see, a different color, 4x hat. Let's go with a minus y hat. So let's draw my coordinates and see what these vectors look like on a coordinate system. So I'll have 1, 2, 3 x hat and 1, 2 y hat. So vector A is going to look like this because I'm going 3 steps to the right and 2 steps up. For vector B, I'm going to go 4 steps to the right and a step down. If there's no number here, it means it's a 1. So I'm going 4 steps over and a step down, which would take me there, right? But now remember, I can take a vector and move it somewhere else and have it still be the same. So what I'm going to do is I'm going to start here. I'm going to go 1, 2, 3, 4 steps right and a step down, which takes me over to here. I'm going to end up there. And I hope you can see now that the resultant is where I started, which is here, and where I ended up, which is there. So the resultant is going to go that way. Let me go use a different color here. So the resultant is that. Right, so I have A here, B here, and A plus B here. Now let's count what the Cartesian representation of a plus b is. I've gone 1, 2, 3 up to here, and then 4, 5, 6, 7 up to there. So this distance here is 7 x hat. Well, shouldn't have an arrow there, so that's the vector 7x hat. And then this vector going up here is obviously only one step, so it's y hat. So you can see that a plus b is 7x hat plus y hat. Now I could have done that easily without drawing by just adding up the components by themselves. So you can see here I have a is 3x hat plus 2y hat, b is 4x hat plus minus 1y hat. So I'm going to add the x hats and put them together. 3 and 4 gives me a 7, and 2 minus 1 gives me a 1. So I end up with the same thing for a plus b. So now I can add vectors algebraically instead of using pictures, right? So sometimes it's easier to do it with pictures, sometimes it's easier to do it algebraically, but here you can see you now have two tools in your arsenal to add vectors. So we've seen how we can represent vectors graphically by just drawing an arrow and in a particular direction. We've shown how we can represent vectors using Cartesians with our unit vectors. So it's some number 3x hat plus 4y hat. Now the third and final way of representing a vector is writing it in polar form, and I'll now show you how we can do that. So to represent a vector in polar form, let me just draw my Cartesians back on here. So I have some point of reference, and that is my vector. I'm gonna call the angle that the vector makes with the positive x-axis the angle theta. That's usually how it's represented in the counterclockwise direction from the x-axis. And I'll call the length of the vector, let's say 5. Right? So this vector, which I'll call A, can be represented as magnitude 5 angle theta. Let me give theta a unit. A value. Let's say it's 30 degrees. So it's a vector of magnitude 5 pointing at the direction 30 degrees from the positive x-axis. So that's the polar representation, and that's it. That's how you represent a vector in polar representation. But it's useful sometimes to be able to convert between polar representation and Cartesian. So let's learn how to do it both ways. I'm going to show you how to do it from polar to Cartesians first. So I'm going to draw my vector, length 5, and I can make this 5 vector by going to the right and then going up a certain number of steps. Remember, that's how the Cartesian representation works. So if I can find out how many steps I'm going to the right and how many steps up, then I will be able to write, let's call this a sub x and a sub y. I'll be able to write my vector in the form of Cartesian coordinates as a sub x hat plus a sub y hat, where a sub x is the number that represents how long this vector is right here in the x direction, and ay is the number that represents the so-called y component of the vector. Now I hope it's clear that this angle right here is a right angle, and that this angle here is 30 degrees as per this diagram on top. So now I can use my trigonometry to figure out what the x components and the y components are. So if you remember, we had SOHCAHTOA was the mnemonic to remember trigonometry, trigonometric functions. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So from here I see that sine 30 degrees is this is the opposite side, that's the adjacent side, and that's the hypotenuse, is AY over the hypotenuse, which is 5. So AY is 5 sine 30 degrees, and I happen to know that sine 30 degrees is a half, so that's going to be 2.5. And if I take the cosine of 30 degrees, I'm going to get the adjacent side, which is AX, and the hypotenuse, which is 5, so AX is 5 cosine theta, cosine 30 degrees, which is 2.5 root 3. Right, so now that I have the x and y components, I can go ahead and represent my vector now. I didn't give this vector a name, let's call it A again. And I found that the x component was 2.5, so it's 2.5 x hat. And the y component was 2.5 root 3, so it's 2.5 root 3 y hat. So what I've done was that I've taken the polar coordinate here and I've converted it into Cartesians here. So now let's look at how we can go the other way. I want now to go from Cartesians to polar. Let's stick to the same example here. Let's say I don't know that the polar coordinates are 5 and 30 degrees, but I do know that the components are, well, let me pick a simpler example. Let's say I have another vector. Let's call it B this time. It's 3x hat plus 4y hat, which means that this vector can be made up of 3x hat and 4y hat. I'll just draw the results in here, which gives me vector B. Left out the vector sign there, and this is a right angle. So it's quite simple to find how long B is, because B is the hypotenuse of this right angle triangle. So the magnitude of B, which I can write using two sets of double lines on either side of it, that means magnitude, or how long the vector actually is. It's going to be the length of this side squared and the length of the opposite side squared, square root. So I'm going to get square root of 9 plus 16, which is the square root of 25, which is 5. Okay, so I found the length of it. Now I can find the angle theta using trigonometry, because this is the opposite side and this is the adjacent side. So tangent theta, which I don't know what it is yet, but I do know that the tangent of the angle is the opposite over the adjacent side. So the angle itself is the inverse tan of 4/3, which is some value. I don't have my calculator with me, but if you enter that into the calculator, you should get a value for inverse tangent. So I've now, let's say it's 37 degrees. I'm not sure if that's, I'm pretty sure that's not the value, but so now I can write B in terms of polars. It's 5 and 37 degrees, or whatever value it is that you get on the calculator. So this takes us to the end of how we deal with vectors, and we will go on to do something called kinematics in the next video.